Right, in this video I'm going to run through the questions for quiz 16. It's the end of the SC25 chapter, which is qualitative analysis that we've been doing at the moment, and you've also got some revision from fuels and the atmosphere. First few questions should be okay. If they're not, when you check the mark scheme, it should be quite obvious. This one, I'll just do it with you. It said the student needs 25 centimetres cubed, that's a volume, of barium chloride of concentration. I mean, they tell you concentration, but you know it's a concentration, and they want to know the mass of barium chloride. Usually when we're doing these calculations, you do concentration equals grams over volume. You do a lot of those types of calculations, and all this is a rearrangement of that same equation, where this time you're looking for grams. All right, so if I rearrange that, I get grams equals concentration times volume. And before you plug those numbers in though, you just need to make sure volume is in the same units. At the moment my volume here is in centimeters cubed, but in my concentration my volume is decimeters cubed. So I'm going to change this by dividing by 1000. Now I've got my volume in decimeters cubed, my concentration is grams per decimeters cubed. All I need to do is multiply these two numbers and make sure I give my answer to two significant figures. I don't know what this is supposed to be. I think it's just literally supposed to be the arrow, so don't let that put you off. You're asked to write an ionic equation. Now it is the test for sulfate, okay, so before I even do this, I know what the answer is going to be. Every time we write the ionic equation for sulfate, you always end up with Ba2 plus SO4 2 minus goes to BaSO4, because we use barium ions to test for sulfate ions, and we form this as a precipitate. But if you can't remember that and you want to work it out using the equation like we were doing in lessons, you absolutely can. Barium chloride is ionic and it's aqueous, so it will split up. Okay, I've got barium with a 2+ charge because it's in group 2. I've got Cl with a minus charge because it's in group 7. Now pay attention to the numbers. That big 3 is in front of barium and chlorine, so it refers to both. And you've got 2 chlorines in barium chloride, so it's going to be 3 times 2. You're going to have 6 chloride ions there. Aluminium sulfate is ionic and it's aqueous. I've got 2 aluminiums, so it's going to be 2 aluminiums in group 3, so it's going to be 3+, and then I've got 3 sulfate ions. That 2 doesn't refer to the sulfate. I've got 3 sulfate ions because I've got 3 SO4 2 minuses. On the other side, barium sulfate is a solid. All right, that means it's not going to split, so it stays exactly as is. And the other side, aluminium chloride, again will split. That big 2 is in front of them both. So I've got 2 aluminium ions with a 3+ charge. And again, I've got 2 times 3, 6 chloride ions with a negative charge. If I cancel what's the same on each side, I lose all of that and I'm left with this. So I've got a big 3 in front of everything, but I can then cancel those 3's, divide across by 3, and I get Ba2 plus SO4 2 minus going to BaSO4, just like I knew I would. You don't need to show your working to get 3 marks. You get 1 mark for the left, 1 mark for the right, and 1 mark for having it balanced. So if you spot straight away that it's the sulfate ionic equation, you can just write this down and pick up all 3 marks. The next one is a 6 marker. We briefly looked at this in class. I know I didn't write out a full answer for you, but if I show you on the mark scheme, it does give you a model answer, and it's so straightforward. Essentially, you're just asked to identify V, W, and X and give some sort of reason. So all of this information here is basically telling you it's an ionic compound. The fact that it doesn't melt at 400 and it conducts electricity as solution, so it tells you it's ionic. But ultimately, to identify, you need to be using this information here. So the pungent gas is going to be ammonia, and if it's giving you ammonia, then it must have the ammonium ion. A cream precipitate with silver nitrate, that is bromine, or the bromide ion. So using this information, you can work out that what you've got, V, must have the ammonium ion if it's giving you ammonia gas, and it must have the bromide ion if it's forming silver bromide. So you can work out that you're forming ammonium bromide. But this is a possible response, okay, and this is in the 5 to 6 mark category. It says W must be ammonia because it turns damp red litmus paper blue. You need to say it starts red and turns blue, not the other way around. It is an alkaline gas. X is silver bromide because you form a cream precipitate. Now you have to mention the silver, okay? When you're doing this reaction, you're adding the silver nitrate. The half equation, if we wrote it out, is going to be this, and specifically the solid is silver bromide. It's not just bromide ions by themselves. To be a precipitate, the bromide needs to be bonded to something. So silver bromide is your precipitate. So you're identifying that it must be silver bromide. If you're getting a cream precipitate, remember a white precipitate would be silver chloride, yellow precipitate would be silver iodide, and then therefore V must be ammonium bromide. Now they've put that in the 5 to 6. Personally, I would say that's probably 5. You have identified everything, but I think you can give a little bit more information. In order to push that up to 6 marks, I would just mention that you know it's an ionic compound, because of the high melting point and the fact that it only conducts electricity, just so that you're incorporating more of that information into your answer. But essentially, if you know your tests, you should be able to pick up 6 marks on that quite easily and quite quickly. The next one here, I didn't do this one with you in class, so I'll go through it now. You're given 3 ionic substances, you're performing 2 tests. The student makes a conclusion, and it says here that none of the student's conclusions are fully justified. So explain which part is justified. So one part from each conclusion must be justified. So say which one that is, and then say what further work you would need to do to carry out to fully justify. All right, so let's have a look at the test they did. They added dilute nitric acid and then silver nitrate solution. This is a test for a halide, and if you're getting a positive result, you are seeing a precipitate, and the color of the precipitate will tell you if it's chlorine, bromine or iodine. The next test they do sodium hydroxide, and then they warm the mixture. If they're warming it, this is typically the test for the ammonium ion. That's what they're looking for there. Or you would do this as the test for a metal ion in solution. So we've used sodium hydroxide twice. So let's have a look and see what they got. So for K, with test 1, they saw a white precipitate. Okay, so that is a positive result. And if the precipitate is white, you can conclude that you have got a chloride ion in there, and the student has done that, so that part is justified. For test 2, they just got a colourless solution and they added sodium hydroxide, and then they said straight away that it was ammonium. That's not true, okay? To prove that it's definitely ammonium, you need to use your red litmus, and it needs to turn blue. Until then, you can't say that it's ammonium, so that is not a correct conclusion. A further test is needed. For the next one, again, they got a white precipitate. Again, that indicates that you have got chloride in there. And then for for the second test, they said white precipitate equals aluminium. Now, aluminium will give you a white precipitate with the sodium hydroxide test, but the problem is so will calcium. And in order to tell the difference between the calcium white precipitate and the aluminium white precipitate, you need to add more NaOH. And if it really is an aluminium, then that precipitate will dissolve. If you add more NaOH and the precipitate doesn't disappear, that tells you it's calcium. So again, they need to do more to prove it's aluminium. For the next one, they got no precipitate when they did the halide test, and then they just straight away said it was sulfate. Again, you can't do that. To prove that it's sulfate, you would need to add barium chloride, and after barium chloride, you should have a white precipitate if it really is sulfate. The next one, they said they added sodium hydroxide, they got a green precipitate, they said that was iron 2. That is a correct conclusion. Okay, so again, if I just show you the mark scheme in terms of how they have written this out, they've given some model answers here. So for 5 to 6 marks, sorry, that light's a bit annoying. For 5 to 6 marks, this would be your 6-mark answer down here. So in K, chloride is justified as it shows a white precipitate, and then it tells you how to justify ammonium. They did the same in L, justified the chloride, but to prove it's aluminium, you need to do this. In M, iron is justified, and then to prove it's sulfate, you would need to do this, and that would get you the full 6 marks. Again, very dependent on you knowing your tests. Next question is about calibration curves. So you just basically have to plot a graph, make sure your scale is correct, so they tell you which axes to use. So display reading is going to go here on the Y. You're going from 180 all the way up to 900. So you might initially think I'll go in 100s. You'll see you run out of space, so you're going to have to go up in 200. So that will be 200, 400, 600, 800, all the way up to 1000 in order to fit in all these points. On this axis, you start small with 0.025, but you need to get the whole way up to 0.5. So again, the only way you're going to fit all that in is if you go 0.1, 0.2, 0.3, 0.4, and 0.5. So you get your first mark for just suggesting a suitable scale, and that scale should take up at least half of the graph paper. Okay, so that's your suitable scale. You get another mark for just plotting your points, and then you get a mark for plotting a curve of best fit. And this is what that curve should look like. So it's kind of a weird curve. And then the next part of the question is, they say you get a reading of 360. What is the concentration? So on my y-axis, I've got reading. I would need to go to 360 here on my y-axis, go across the curve, go down, and whatever value I have on x is the concentration of potassium ions. The next question is moving away from SC25 and back to CC16. This question came up in your mocks. It was difficult. I don't think anyone got any marks on this, and I can see why. They're asking you to improve the method to make the results more valid. Majority of you spoke about repeating the experiments and using different plants and all the rest of it, okay? But we need to look at what they are actually trying to achieve here. They are trying to check the effect of acid rain, and when they're doing this, they're just taking hydrochloric acid with a pH of 2 and pouring it on their plants. Now, hydrochloric acid with a pH of 2, is that representative of acid rain? Well, no, it's not. If you think about how acid rain is formed, it's sulfur dioxide that dissolves in water and forms sulfuric acid. So it would be better to use sulfuric acid instead of hydrochloric, as that's what acid rain is actually made up of. Also, acid rain has a much higher pH than 2. Acid rain is a pH of around like 6. 2 is way too acidic to mimic acid rain. So you could say use an acid with a higher pH, or use sulfuric acid instead of hydrochloric, because both of those closer represent acid rain. And the other thing they allowed you to talk about was the control. They used pure water as the control. A better control would just be normal rainwater, because rainwater is not going to have a pH of 7. So they're trying to compare acid rain with normal rainwater. Pure water, again, with a pH of exactly 7 is not indicative of normal rain. Yeah, and effectively they are all the things that they would accept. Oh, there's a few other things you can get there on the mark scheme, but they're the main points. But yeah, no marks for just saying repeat. This question here also came up in your mocks. It was quite poorly answered. Explain the trend in viscosity. A lot of you just stated the trend. Again, so you're told that as you go down the group, viscosity increases. They want to know why. That's what's being asked. So we know viscosity is their how easy they are to pour, and they're saying they're getting more viscous. That means they're going to get harder and harder to pour. They become thick, sticky liquids, like bitumen will be tar that you use for the roads. They're thick and sticky. They're difficult to pour, but they want to know why. So we know that as you go down, you get an increase in size, so the molecules are getting bigger. But you need to link that to intermolecular forces. So we're going to say the molecules are getting bigger. That means the intermolecular forces are getting stronger. If I were to draw, that is one molecule, I'll call this a second molecule. The longer they are, the more intermolecular forces I can have between them, and therefore the stronger those intermolecular forces will be. If you think about pouring a liquid, all the liquid particles need to be able to roll over each other. If there's really strong forces between those particles, it's harder for them to roll over and around each other. It becomes harder to pour. So the bigger the molecules, the stronger the intermolecular forces, the harder the particles find it to roll over each other, the harder it becomes to pour. All you actually need to say is molecules get bigger, intermolecular forces between molecules get stronger. Another question on your mock that you either knew it or you did not. You need to deduce the molecular formula. To work out molecular formula, you have to go through 3 steps. In the first step, you get the formula mass of the empirical formula. You're told the empirical formula is CH2. The formula mass of CH2 is going to be 14. In step 2, you take the formula mass, which you're given in the question, 56. You divide that by your answer to step 1, you get an answer of 4. In step 3, you take the empirical formula, CH2, you times it by 4, you get C4H8. This is something we would have done in CC9 when we learned about empirical formula. We also learned about molecular, and you follow those 3 steps. But what we've worked out here is all of this information is for Y, so we've just worked out that Y is C4H8. We're not asked about Y, we're asked about X. So in order to work out what X must be, you're going to have to add these 2 together to work out X. So C6 and C4 is going to be C10, H14 and H8 will be H22. So essentially X is C10H22, then X underwent a cracking reaction to form hexane and to form butene. This one came up on a quiz. It was quite poorly answered then. You're trying to work out the percentage of oxygen in air, and this is a typical apparatus that you would use to do that. So what you've got is you've got some zinc in this little glass tube, and in syringe A you've got dry air, and syringe B you can see is fully pushed in. There's no air in B. Now dry air just means there's no water. You've removed the water from the air, so all you would have in there is just nitrogen. You'd have your oxygen, you'd have your argon, you'd have your carbon dioxide, but you wouldn't have any water vapor. And what you do is you'll push this syringe in, and the air will pass over the zinc and into the other syringe, and then you push the syringe B in and pass the air over again, and you just keep passing the air back and forth over the zinc. And if you apply heat to zinc, what it will do is the zinc will preferentially react with the oxygen. It won't react with nitrogen or argon or CO2. It will just react with the oxygen, and all those oxygen molecules will end up forming zinc oxide, and they'll be removed from this volume of air. And what you'll find is as you're pushing the air over and back, you end up with less air as all of the oxygen is removed to react with zinc. If you know the volume that you started with, let's say you started with 200 centimeters cubed, and at the end you end up with a value of 160, you know that 40 centimeters cubed must have been the oxygen that reacted with the zinc, and then to work it out you take 40 over the original volume 200, times it by 100, and you'll get an answer of 20%. So in terms of where your mark's coming from, you heat the tube where the zinc is, you're passing the air over the zinc, you keep going until the volume stops changing, and then once it stops changing you calculate the difference between the starting volume and the end volume, and then you can do your little calculation. The last one here also on your mock was really poorly answered. Okay, it's just content that you have to learn. You need to know that the impurity is sulfur. That's the impurity, and when you take a fossil fuel you have to combust it so it releases energy, and to combust a fossil fuel you must react it with oxygen. When you react sulfur and O2 you form SO2. Now just that alone will get you all 3 marks, but if you want to go further you can say the sulfur dioxide dissolves in water to form sulfuric acid, leading to acid rain. Some of you said sulfur dissolves in water. That's not true. The sulfur reacts with oxygen during combustion of the fossil fuel, forms SO2, the SO2 dissolves in water to form acid rain. That should be part of the next quiz. Sorry, so question 40 should be part of the next quiz. I just put the title in the wrong place, so we cannot do question 40. That's equilibrium.